Okay, so I'm Terhikki Manninen from Finnish Meteorological Institute and shall start this latest section of this workshop. I'm happy that there are still people here because we have been listening quite a lot of things and it's late hours already. So our topic is challenges of surface albedo validation and examples of European products. GlobAlbedo from ESA CCI and Clara A1 Sal from CNSA. I might have taken also an example from this Geoland tool, but the trouble was that I did not find early enough the right pages. I was circling in the Google and it went all the time to old Genius pages instead of Copernicus. But mainly this GlobAlbedo validation is more similar to this Geoland validation than with this Clara. So these examples maybe compensate each other nicely. So first is albedo. If somebody is not familiar with it, it is the ratio of the hemispherically reflected radiation to the. So we have two extremes. The black sky albedo, which means that the coming irradiance is only the directional component. And then we have this other extreme, white sky albedo, where this incoming irradiance is completely diffuse. And the normal blue sky albedo is then a weighted sum of these two. The weighting factor V is the fraction of direct illumination. So these three albedos are sort of the things that we are discussing. For modeling purposes, usually it is this black sky albedo that is most needed, because it has no component coming from this atmosphere. The unfortunate thing is that the black sky broadband surface albedo can't be measured at the surface of the globe, because the atmosphere affects the broadband measurements. So even if we make a satellite product called black sky albedo, we cannot measure it in situ. And for the white sky broadband surface albedo, it's the other way around. The satellite cannot really thought to be measuring it, because white sky albedo corresponds to a situation of completely overcast sky. And the satellite in optical wavelengths does not see through the cloud cover. So then we can measure the white sky albedo in situ, but we have no corresponding white sky albedo product directly from satellite measurements, otherwise than defining first blue sky and black sky albedo. So the blue sky albedo is the composite of this black sky albedo and white sky albedo, and that can be measured both in situ, and we can think that the satellites react to the blue sky albedo, because we have both the normal direct illumination and some part of diffuse illumination included. And then coming to very simple practical things, because we have had a long day and there have been these more theoretical aspects already covered, what validation means altogether, thinking about several products, but now we think everything from the point of view of surface albedo. But many things are common with other things, other parameters validation. So first is the accuracy of the validation data that we have to think about. So our validation will never be better than is the accuracy of the in situ data we are using for validation, or whatever data we are using, whether it's in situ or something else. So that's the the best accuracy of the validation, not necessarily the product accuracy, but the validation accuracy. Then we have to worry about spatial coverage of the validation data. So if we have a global product, where it is really validated, then the temporal coverage of validation data. If we have a product covering something like several decades, do we validate it throughout this period of time, or only the newest part, or some other part? Then we have to worry about seasonal coverage, so that are we validating it also in winter in difficult conditions, or only in summer perhaps. There is this resolution difference between product and validation data. So if we have in situ measurements, they are often covering rather limited area, and if we have these satellite products, they are seldom very high resolution products, especially if they are global products. So can we compare without difficulties these two, and what kind of difficulties we actually mean when we compare these two? Then there is this trouble of representativeness of the validation measurement side. So we validate in a numerable number of places. So do we cover all line cover classes, for example? Or do we have just a biased subset? And then the real problem for this surface albedo validation, there is no actual validation data available. As I said, for black sky albedo, we cannot measure it on the globe. If we were living on the moon, we could measure it in situ, but not on the globe because of the atmosphere. So then we have to think about something else. Either we have to validate a related parameter, like we don't take the black sky to validate, but we validate the blue sky. The satellite blue sky product versus the in situ blue sky measurements. Or we compare non-identical parameters. We compare the black sky satellite estimate with blue sky measurements. But then we have to assess somehow this inherent difference between these two products. No, this was the trouble for the person carrying out the validation. But then another thing is how to interpret the validation that has been done. So you take the validation report and you see the statistics which is there. And there is a certain accuracy, absolute or relative given, or maybe the distribution or something. But then the question is, does it apply to the whole spatial coverage of the product? Is it so that in some geolocations the accuracy is what is given in the validation report, but in other places it is something else? Does it apply to the whole temporal coverage of the product? If we have a long time series, are the early products as accurate as the late products? Does it apply in all seasons? So even if we are measuring and validating both in summer and in winter, autumn and spring, is the accuracy the same in summer as in winter? Does it apply throughout the day? If we happen to have a satellite that sometimes we get only morning retrievals and sometimes we get midday retrievals, is the accuracy dependent on this or not? And does the accuracy description we find in the validation reports, does it describe the accuracy of the methodology used, or does it describe the end product? And does it apply to all land cover classes that can be found on the globe? Does it apply in rough terrain, like mountainous areas? And does it really apply to the parameter of interest or to only a related parameter? So if the validation has been carried out using blue sky data, with blue sky data in situ measurements, what does it tell about black sky albedo accuracy? Or does it tell anything? So I really recommend that check what is mentioned as known issues on web pages or in validation reports and publications. And also, it is a good idea to plot the data before starting to use it. Make some maps, thematic maps of the data. The human eye is quite good in catching some artifacts out of an image. The data providers typically want to describe as much as possible. They present really honestly known issues, but if you have a global product, it's very clear that you can in a validation report of limited size tell everything that concerns every single place on the globe. So that if your place happens to be some special place, it might not be mentioned that there is some extra trouble related to that. So, first of the accuracy of the validation data. Pyranometers are typically used to measure the irradiance and the reflected radiance. And the instrumental accuracy, as I mentioned, it defines the minimum error of the validation process. But on top of that comes another set of errors. And outdoor measurements are really challenging because thinking that we have all kinds of weather conditions, we need ventilation and heating to guarantee all year-round operation. Horizontal orientation is necessary for hemispherical measurement accuracy. And then, unfortunately, the upwards-looking pyranometer is especially sensitive to trash, dust, etc., accumulation with wind. And in some places, birds, unfortunately, like these pyranometers. So that is a challenge for continuous measurements. And regular calibration and maintenance is essential for that purpose. And we have quite many unmanned stations. So you have to realize that the unmanned stations can't guarantee everything at the same level as manned stations. And unfortunately, some locations are such that they are close to forests or rough terrain, so that there is some shadowing. If it is permanent, like mountains, it can be taken into account to some extent in the in-situ measurements. But with forests, even that is more difficult. Now, example of spatial and temporal coverage. The BSRN network is used for albedo validation, but as you see, the measurements are continuous, but they represent only a small area of the globe because they are pointwise measurements. Another possibility is to cover a larger area, but seldom, throughout dedicated campaigns. Like we had a Snorted campaign in 3 years in Finland. We were flying in an area of about 50 kilometers by 50 kilometers. But then it is not every single year, every single month that you get this data. Example of the seasonal coverage problem. It is difficult to get a statistically sufficient amount of validation data in some places because they might have a high cloud cover fraction, typical, like rainforests or polar areas. You get very little data to that kind of places. Then there are areas which typically have high aerosol optical rate, which also causes difficulties for the atmospheric correction. These kind of places are deserts, and then in generally India and Southeastern Asia, for example. And then areas with typically low sun elevation are really problematic because the instrumental accuracy goes down for the in-situ measurements with increase in sun zenith angle, and also the atmospheric correction of the satellite products becomes more challenging the lower the sun goes. So polar areas and a large part of the boreal zone are areas where you have typically difficulties caused by the low sun elevation. Then there are these unmanned measurement sites of in-situ measurements in areas of high risk of human or animal violence to the instrumentation. Either there are areas that are unstable politically or for some reason, but also animals are really problematic, like the polar bears are known to eat almost anything, like electric cables and that kind of things. So validation site representativeness. The pyranometer mass are usually in continuously operated stations like WMO stations. And typically they are defined so that the terrain is flat and the preferred land cover is like grass or barren land or agricultural fields. Very seldom we have pyranometers operating continuously above forests. And what is even worse is that it is impossible to have continuously measuring instrumentation in wetlands because the wetlands are so unstable basis for construction. And some measurement stations are located in mountainous areas, for example, this ESRP in Switzerland, and the in situ data probably can be corrected very, very well because the mountains don't move. But unfortunately, the satellite pixels are not always located exactly on the same place, for the polar satellites at least. So using this kind of in situ data together with satellites is challenging. Now then to the validation side representativeness. Our pyranometer here is registering the incoming radiation and the reflected radiation above this nice little spot of grass. But what the satellite is detecting is that there is also some forest here and a lake here. So that our satellite is not thinking that we have a site of grass only. The satellite sees much more. So how can we compare these two with each other? This needs more work, and very high resolution land cover maps can be used to some extent to help in this situation. Now then about this land use class program. As I already mentioned, the wetlands are not suited for construction or mass for continuous albedo measurements. And unfortunately, the wetlands vary with season also markedly. And northern latitudes at least are full of wetlands, but not only the northern latitudes. There are also places elsewhere on the globe that have quite a lot of wetlands. So to show what it is all about, let's have a tour on our nice globe with examples. Starting from the north, these pulsar wires, which are typical of the northernmost latitudes in Europe. This is from Finland. Then we have the more typical forested wetland in Finland. And then we go abroad. I think this is from Britain. It's more like grass-like and low vegetation, salty grass-like wetlands, sand, mostly with these small ponds, and forested wetlands, could be boreal zone, looks like that, and deciduous forests with wetlands, and rice fields. And as everybody knows, the rice field has a seasonal variation quite high because of the crop. I mean, first it starts with tiny little elements coming from the ground, and then you have at the end you have something to harvest. So this wetland certainly changes quite a lot with time. Also, then more shrubby places, mixture of several classes, like sandy areas and bushy and forested areas. And this kind of very strange looking vegetation, you can just imagine that if the season changes in this kind of area, the fraction of open water certainly varies. And sometimes you have quite a high fraction of open water in wetlands. In some places you have so-called seasonal lakes, so that the lake disappears for some months and then it appears again. So if it is a large area, it really matters from the point of view of albedo. And the seasonal variation in the reflectance is also often high in places like in the northern latitudes where you have real winters with freezing and covering, like this is frozen wetlands. And to end this tour, this is from northern Lapland, typical Aapamaias, where you can see the striped structures. So this, in summer, the stripes grow grass. Sometimes you have tiny little trees on them, and between the stripes it is open water. And now in winter it is frozen, so that you can really drive with a snowmobile on this. In midwinter it is more or less white altogether, but this is from the melting period. And in the melting period in the morning it is usually completely white between these stripes, but during the day when the temperature goes up and the sun starts to warm up, also this this surface, the diffusion from the water beneath makes this darker. And so that in the afternoon it is dark, and in the next morning it's light again. So quite a marked change in the albedo, but no continuous measurements for in situ data. So, to summarize this part is that the validation of surface albedo is especially demanding in cases of low sun elevation, high cloud cover fraction, high aerosol optical depth, snow-covered area, especially in periods of rapid changes, rough terrain, very heterogeneous land cover and wetlands. So that was about the general approach to albedo validation, but then as an example, starting with this GlobAlbedo product and known issues. Here you have this GlobAlbedo product web pages. It is easy to find everything on the pages, and the validation report also. And the validation report is really thorough, and very clear examples are given of known issues. Like here, you have these boxes 1, 2, 3, and 4. Starting with box number 1. It's in Europe. You can see that there is a very strange border with snow cover and not snow cover. And they also tell in this validation report these known artifacts that you can easily detect visually. One problem is the snow detection. One problem is at polar latitudes to fill in gaps due to low sun angles. And one problem is missing satellite data at high latitudes or very southern latitudes. And these artifacts that they have given, box number 1, was that this area does not accurately follow seasonal albedo cycles due to problems with snow detection. And additionally, they comment that the only year unaffected by this artifact is 2005. So it is not some trifle at all. You have to realize that it exists. Then another thing is number 2. It is here in Alaska, and the human eye can tell that this doesn't look a sort of geophysical border. And what they tell is that a wedge-shaped feature does not follow seasonal albedo cycles. This effect is not always apparent, though when present it is extremely obvious. And it occurs irregularly throughout all GlobAlbedo dataset years, 98 to 11. Then boxes 3 and 4. They are northern Canada archipelago and northern Siberia. Very strange to think that there is snow south of this straight line and not snow north of it, and the same in Canada. And what the validation report tells is that snow detection-related artifacts occur commonly throughout the GlobAlbedo dataset. And still one issue in the Antarctic. You can see in this figure that certainly this is not really the true thing at all. It is an artifact. And they say that the polar regions demonstrate significant irregularities, with commonly occurring missing data, SWOT artifacts and prior artifacts present in all dataset years. So, as I said already, polar areas, low sun elevation, snow detection, they are the difficult things. Then about this related parameter validation. If we are after the accuracy of the black sky albedo, what does this blue sky albedo validation tell? For example, here if you think that the blue sky albedo is something like 0.22, like here it is in this desert rock place. The tower measurements are the black ones and the GlobAlbedo is the red one. We could think that this comes from a case that we have 90% of the irradiance is direct irradiation. And then only 10% comes from diffuse. Or we can think that 80% is direct and 20% is coming from diffuse illumination. But this means that there is an uncertainty that whether the black sky albedo is 0.22 or 0.2, so it's 10% already. And how often does this occur, this difference between 0.9 and 0.8? Depends, of course, on the place. But one example is in Sodankylä. This was in 2004, a perfectly clear day. And as Sodankylä is north of the polar circle, the sun is always relatively low down, but the albedo retrievals are restricted to this 20 degrees elevation or 70 degrees zenith angle. But still having this variation of the ratio of diffuse and global radiation is from 10% to 20%. So this is something one has to take into account. It's again the polar areas that are the difficult ones because the sun elevation. Then seasonal coverage of validation, the GlobAlbedo product. Here shows a glacier boulder where we know that the winter is a local one. Good, nice snow cover. 0.8 about this level of midwinter albedo. And again, the tower is the black one and the GlobAlbedo is the red one. I don't know exactly if the reason is this, but we can see that there are winters when both reach the same maximum value very nicely, like here. But then there are winters that the satellite retrieval never reaches the highest values. And it is possible that this could be caused because of cloud coverage, so that if you don't get any satellite data when it is midwinter, then you never get the highest values at all. If the winter just happens to be so cloudy. I don't know whether this is the problem, but it could be like this. But this is a certain case. This is from Estonia, Toravere. It's a place where the tower is detecting mostly open area, so that in winter they have nicely snow, and again this albedo is 0.8 and even above. But this satellite data never reaches that high values because there is coniferous forest so close by. So that a large part of the satellite pixel is masked by this forest, which has much lower albedo than the snow. And now Aku will go on with this Clara A1 cell.
Thank you. Hello again also from my part. So now having looked at the GlobAlbedo, it's time to also take a look at some known issues in the Clara A1 cell dataset. And the main limitation in this dataset was that the aerosol optical depth we used in calculating the surface albedo was set to a constant level of 0.1 at 550 nanometers throughout the dataset. And we did this consciously because we did not have a universally valid aerosol dataset covering 1982 to 2009 at the time of the generation of the A1. So we thought that it is best to select one value which we know, so that in post-processing later on we can think of and try to devise ways to correct the effects if major problems or artifacts occur as a result of that. So actually we have done it. There is a post-processing correction. If you're thinking of using the Clara cell dataset, you might consider looking at the paper there in the middle by Manninen et al. In last year's EUMETSAT Meteorological Satellite Conference proceedings. But I also should point out that the aerosol problem is mainly limited to the mid-latitudes. So in the high latitudes, aerosol optical depth doesn't really vary all that much from our set value of 0.1. So we haven't seen any major problems in the validation or in using the data for cryospheric studies, so the dataset should be perfectly okay for use closer to the polar regions. And I will note that, of course, in the next iteration, we are now working on the dynamic aerosol optical depth correction for the atmospheric correction part of the algorithm. But just to look at what happens in Clara A1 cell as a result of this, this is a plot of the deseasonalized surface albedo anomalies in the monthly mean products. And anomaly, of course, means the deviation of a monthly mean albedo from its long-term average. That's the definition. And you can tell, okay, and I should point out, of course, that this is kind of a Hofmöller plot. So time is running along the x-axis month by month, and every row in the y-axis corresponds to a latitude band on Earth. So we've averaged all the albedo retrievals over each latitude band for each month, and those then form the individual pixels in this image. So you can tell by looking at this that there seems to be something going on in the mid-90s, in the mid-latitudes. A sudden increase in albedo anomaly. And if you look at the point where it originates, it looks like it's 1991 in June. Does anybody have a guess of anything major that might have happened in June 1991? Right?
Volcanic eruption.
Right. Mount Pinatubo in mid-June 1991 at roughly 15 degrees longitude, the second largest volcanic eruption in the 20th century. So obviously, the additional aerosols in the atmosphere after that event are not corrected because we don't have a dynamic correction in this version. So of course that will mean that we then get a substantial positive surface albedo anomaly for the mid-latitudes that persists for a long time, and then added onto that in 1994. 1994 was a particularly active year for Saharan dust storms. It's been covered, it's been measured by in situ measurements of Saharan dust over Barbados, for instance. So those two events put together result in this large anomaly area, which kind of is very evident if you look at the mid-latitude surface albedo also in the product. Then once those events die down, we return to much more normal conditions where the anomalies are quite acceptable then at 0.01, 0.02 mainly. The higher latitude anomalies are usually, well, almost always related to just year-to-year variations in snow cover. So those are to be expected. It's just these mid-latitude issues that we have to investigate, and I think that this is the reason, and these two events are the reason why we see these anomalies. So it's always good to, like Terhikki said, to thoroughly read the validation reports, read the papers. We've written about these events. This actual figure is from the paper describing Clara A1 and the associated discussion about the anomalies and their causes is available there, and we of course urge people to read them. And it's good to be aware as a user also that these things do occur, and they usually occur for some reason, of course. Okay. So Terhikki mentioned that if we measure or we retrieve black sky albedo from satellites, but we only have blue sky albedo measurement data from Pyranometers on the ground, what does that mean for the comparability of the two? Can we still use the blue sky albedo data to validate our black sky albedo, even though, strictly speaking, they are not quite the same quantity? So we did a study on that, using various sun zenith angles for various different land cover types. So here on the x-axis you have the black sky albedo as it was calculated in our simulation study versus the, oh wait, sorry, that was the other way around, isn't it? This is the black sky albedo, and this is the blue sky albedo. So this would be what the Pyranometers measure, and this is the kind of the inherent property of the surface. And you can tell that for the majority of the sun zenith angles, the differences are quite small, and they are not really dependent on the actual, or not terribly dependent on the magnitude of the albedo itself. When the sun zenith angle grows very large, then the atmospheric path length of the radiation through the atmosphere grows very large, and then we begin to see larger differences. These points, these line-like points in red are from the highest sun zenith angle. So then you begin to see the difference. Fortunately, we don't try to retrieve the albedo at low sun zenith and high sun zenith angles in Clara. So in general, we can say that the comparability is good enough that we can use the Pyranometer data. This was for all the diverse line cover types, and here you see just a case example of grass. They are quite similar for the most part. Then you can also look at the relative difference if you have, well, within the study we also calculated ways of let's say, quantifying through a regression the difference if you know, or if you have measurement data from your pyranometer containing both the direct and the diffuse components of the radiation field, then you can kind of use this equation with the regression parameters to estimate what would have been the black sky albedo out of the blue sky albedo that you measured. So you need to have the blue sky albedo and these direct and diffuse radiation field components to get that. But it's a long day, so let's not go that much deeper into the details. I think we've all seen enough equations for this time. And then just a mention that the Clara A1 cell contains a separate topography correction for the ABHRR data, partly because the pre-processing of the ABHRR data usually assumes a flat Earth. So that means that first of all, for snow or mountainous areas, the pixels might not be exactly in the right place, because the actual place where the radiation field has kind of left the Earth's surface on its way to the satellite sensor might be different when it's calculated for a flat surface relative to the actual topography that was present. The second part is, of course, that the high topography creates very challenging conditions for calculating VRDF corrections, and also the sun and shade, and whether or not the sun sees a particular mountain slope, whether or not the satellite sees a particular mountain slope. Those are problems that need to be addressed, and we've tried to do that. So here are just a couple of example images from the Alps. I'm not exactly sure which. This is probably the retrieved albedo here in the middle, uncorrected, and this one is then the corrected one. So it actually does. We don't have a color bar here, but there is quite a bit of difference, especially for the, let's say, the middle area of the Alps, where you have the really deep, high topography varying a lot from pixel to pixel. But the details of the correction method are in the ATBD of the product if you're interested, or you can just come have a chat with us. Okay, to finish off, here's some validation information that is available regarding the products we've talked about here. For GlobAlbedo, you can see, for all of them, you can see the websites there, and the associated validation reports are also available through those websites, and it's a really good idea to look at them. And just about all of the data providers also have help desks through which users can directly contact the people who've made the products and ask for why is there a feature X in the product for this region and time of my interest. And the people are, of course, all the product producers are generally very willing to help users, because having users is why we make these products in the first place. Okay, so if you have any questions about albedo validation, now would be a good time.
Thank you.
Okay.
Yeah. Are there some comparison of these three data products in terms of consistency and stability?
I think that there are such studies in preparation, but there are not those published studies as of yet for a really long term. There have been for a limited time there have been some studies. We compared the A1 cell to MODIS for 1 year during the validation practice, and there have been some ongoing efforts to expand those. Anything else? If not, we've prepared, since we have maybe a little bit of time, we have a couple of frequently asked questions here.
If you ask the question,
Okay. Okay. So now we're kind of talking like a user asking the provider of something. So the first question is, okay, So I want to use these albedo products. What's actually the accuracy of the validation instrument?
So usually the parameter accuracy is such that one expects to get 2% accuracy for hourly measurements and 1% for daily measurements, for 95% confidence level. But one has to take into account that this is not achieved above, let's say, about 60 degrees zenithal. And also, if you have extreme hot weather or cold weather, then the accuracy is not quite the same.
Okay.
So, and it's your turn to answer the next question. And the global representativity, point-wise validation, can you motivate us?
For all the in situ data, it's necessarily a point-wise validation, but we can at least try to achieve a situation where we have in situ data for all the major land cover classes, maybe excepting wetland where it's difficult, so that even though we can't really cover the entire Earth's surface from the point-wise measurements and their comparison to satellite products, we can at least try to say that we've sampled the different regions of the Earth and different land cover types, including snow and ice, well enough that we have some handle on what the validation accuracy and what the product accuracy is for different archetypes of the land surface of the Earth. And that's currently probably the best we can do against point-wise in situ data that doesn't really cover even all areas of the Earth.
So useful but not sufficient?
Useful but not sufficient. It's still necessary to compare different satellite datasets as well.
And satellite instrument aging, effect on product accuracy, what can you say about that?
For surface albedo, this is a really important point, simply because the albedo that we retrieve is directly related to the radiance measured by the satellite. So if there are calibration jumps, if we use input data that has not been intercalibrated but is from multiple satellite sensors or is from a single mission that has gone on for a long time, so even a single instrument ages and decays with time, so that you may have a situation where a single instrument says at the start of its life that okay, this ice sheet has an albedo of 80%, but at the end of its life it will say that the same place has an albedo of 70%, even though there is no real change except that of the instrument itself. So the advice there to users is to examine if the dataset is built on an intercalibrated FCDR. No matter actually which dataset, it's always a good idea when you're looking at land surface variables.
But do you check this stability of your product?
For A1 cell, we have calculated this for ice sheets with the assumption that the ice sheets are stable in time in regard to their albedo, and for A1 cell, at least we can say that yes, the dataset is stable within, let's say, 7% relative.
Okay. And rapid phenomena and effect on validation. I mean, if you are interested in very quick melting or something, what can you say?
This is a problem, especially for surface albedo, since we can't, in optical wavelengths and optical instruments, can't see through clouds. So if you just try to generate a daily global mean product, it will be very sparse, because the cloud cover globally is really big, and it's very big also for the snow-covered higher latitudes. So this leads to the problem that we almost always have to aggregate several days of data to get some kind of a representative albedo retrieval for the high latitudes that are snow-covered. However, this unfortunately also leads to the problem that we then lose some of our capacity to track really rapid changes, because we have to do the aggregation, we have to do averaging, so we necessarily lose some of the information there. But this unfortunately cannot be fixed technically. We need some way of getting rid of all the clouds if we wanted to do that, and it's not really feasible to do that.
But what about microwaves? Can you help it with microwaves?
Yeah, Microwave instruments can see through clouds mostly, so if you have microwave instruments and you can devise a way of looking at the brightness temperatures of the surface and finding correlation to interesting variables like albedo, then you can try to circumvent this problem. But that's, I guess that's a work in progress at the present time. All right. Thank you. That was all from our part.
Thank you.